Okay, for this last part, we're going to talk about correlation coefficient, which is just a number. Again, we will find in our multi-view calculator. It just tells us how strong our line of best fit or our linear regression model is. And so it is a range between -1 and +1. Now, the negative just tells me that it's a negative correlation. That means our slope is going down. Like as time goes up, it makes something go down. So the negative just tells me the direction. And then again, your positive just says that we have a positive correlation. Now, when you have a 1 or -1, that is like a perfect fit. So that's like perfect. Anywhere from 0.8 to 1 is considered a strong, or if you're looking at the negative side, -0.8 to -1, we would say that's a strong correlation. And then you can see between 0.75 and 5, there is a correlation, but it will be considered weak. This correlation coefficient, we use the R to represent that value, and it just indicates how reliable our line of best fit is. So let's take a look. Again, in your notes, make sure that you understand that when R is 5 or less, it is weak. And if it's 0.8, oh, that should be a point right here. Let's add that to here. So 0.5 or less is weak, and then 0.8 or more is strong. And you can see in these little pictures like -1, it's going down, and this is pretty much a perfect negative correlation. This one you could say is about -0.8, and it is pretty strong. The points are clustered together and they are going down. Okay, let's move in the middle, 0. There's no correlation at all. You can see that. You can see this perfect positive correlation. It's going up. It's like it truly has a constant rate of change. Let's look at our example again of the amount of hours we study for our math EOC and the actual EOC score. So you're going to have all this data in your calculator. Again, remember your X values are list 1, your Y values are list 2. All your order pairs are lined up correctly in your calculator. To find your correlation coefficient, you do exactly what we did to find our linear regression model. And as you scroll down, here again, remember your A was your slope and your B is your y-intercept. And then here's the R value, just the single R. This is your correlation coefficient. And we're usually going to round to the 10th or more likely the 100th. So we can see 0.94 is pretty strong, and you can see that most of these data points are clustered close together, and they are pretty much hovering around your line of best fit, that linear regression model here. So the 0.94, and maybe we should say R equals that. This just tells me that this line of best fit is a pretty good fit to represent our data. And so I'm going to say that it is a positive, strong correlation. And again, remember, correlation deals with measurable data, data that is quantifiable. Okay, let's take a look at another one. Here we have extracurricular activities, how many activities that you take, and compare it to your GPA. Is there a relationship between the number of extracurricular activities you are in, and does it have an effect on your GPA? So we're going to use our multi-view calculator. We're going to get our linear equation. We're going to get the R value, and then we're going to use that to predict the GPA when we have 3 extracurriculars, 8, and then know how many, if we have a 3.7, how many extracurricular activities probably did we take. So I have already calculated in the calculator, but again, you need to practice this, so make sure that you have paused and input the data yourself. And then when you get to second stat, you're going to scroll down and you can see my A value is 0.3. So that's going to be my slope. And then your B value is about 2.2 right here. And so that's my starting point. Then when you scroll to the R, you can see that your correlation coefficient is 0.95. So that's pretty strong. So I would say strong and it's positive. Okay, now we can use this to make some predictions. So 3 extracurriculars, and I will say that 3 is going to be interpolating the data. Let me back up and look at so 3, you can see these values are given to us. So we're going to put it in the equation, but we are interpolating because we have those values that are given to us. So I'm going to just input 3 for X, which stands for extracurricular activities. And we're going to see what we would make on what is our GPA. So 0.3 times 3 plus the 2.2. So this gives us a GPA of 3.1. Now 8 was not in the range. You can see 5 was the highest in of our extracurriculars. So let's just say we have somebody that's really above and beyond, and we're going to put in 8 extracurriculars. This is extrapolating data. We're looking outside the range. And we get a 4.6. So you can see those people are above and beyond. Now 4.6, some schools may just say 4 is the cap, but a lot of schools, especially taking those high level classes, you can actually make over a 4.0. Now we're going to predict how many extracurricular activities if we have a GPA of 3.7. So we're going to plug in 3.7 for our output because our output was our GPA. And we're going to say 0.3 times X plus 2.2. So we're going to subtract out 2.2 from both sides. I'm running out of space, so that is easily calculable. So we get 1.5 is equal to 0.3 times X. Divide each. And we get about 5. Okay, so 5 extracurricular activities gives us a 3.7. Okay, let's look at one last example. Here we have the number of visits a baseball or a softball player visits the batting cage. And then here's the season, our batting average. So we're going to put in list 1 is going to be the X values are how many times you practiced. And list 2 will be in the actual games. So when we put this in, you can see I need to go all the way out and get some number here. Okay, so sometimes you can't round to the 10th or the 100th. Sometimes you may even have to go out to the 1000th place. Okay, just to make sure you don't round too quickly. So, and you can see that our R value is 0.957. So I'll round it to the 100th, 0.96. So this is going to be a strong positive correlation. So that means the more times I practice batting, the better I did in the actual game. So we're going to plug in 12 into our equation here and get out what our batting average would be. So 0.001 times 12 plus 0.2 gives me about 2.212. So visiting 12 times may not be the best outcome. So let's see our batting average when we visit 120 times. .001 times 120 plus 0.2, so 0.32. Now we're going to predict the batting cage visits with a batting average of 0.255. So this time we're going to plug in something for the outcome and see what we have to put in to get the 0.255 batting average. I'm going to subtract out 0.2. we're going to divide. I want to come up here to show my work. So 0.055 divided by 0.001 gives us 55. So 55 visits will achieve a 0.255 batting average. Okay, here we have a table. Our list one, our X values, is the total amount of fat in something to eat. And then the calories is going to be our output. So let's see what we get here. When we put this in our multi-view calculator, I got a slope of 13.3 and a starting point of 142.6. Our correlation coefficient, 0.99, that is pretty strong there. So that is a strong positive correlation. And then whenever we put in 25 grams of fat, how many calories is that going to give us? So 13.3 times 25 plus 42.6 gives us calories of 375. So you can see the more fat, the more calories, which is energy that we're going to have. And then whenever I put in 50 grams of fat, how many calories will that give us? Again, calories is energy for our body to burn. And if we don't burn it, then we store that energy. So this is 807 calories and 807 and 6 calories. So let's put our units there, Miss Thomas. Now, if we have something that's 350 calories, how much fat was that? So we're going to subtract out the 142.6. I am going to use my calculator and subtract that out. And I get 207.4 is equal to 13.3. We're to divide each side by the 13.3. And we get 15, I'm going to round, about 15.6 grams of fat.